Light's nature as a transverse wave, first deducted by Robert Hooke in the 17th century, enables it to have unique properties that are not immediately apparent. Indeed, because light moves as a wave, the orientation of the light waves, which can be taught as the angle between them and a fixed point, normally the vertical axis, can influence how they interact with some objects or mediums. Indeed, some objects are able to interact with light differently based on the inclination of the light waves traveling through them. This is a phenomenon known as polarization, or the selective filtering of some orientations of light. Normal light emanating from the excitation of electrons is usually unpolarized. That is, it does not have a single angle. It can usually be thought of as being composed of all possible light orientations equally. Polarized light, in comparison, is normally only composed of light waves moving on a single axis. The intensity of a polarized light is also smaller than that of the initial light. Indeed, assuming a perfect polarizer, the intensity of a polarized light is given by Malus's law. Final intensity is equal to initial intensity times cos squared of the angle between the light's polarization and the axis of the polarizer. For unpolarized light, this value is usually half of that of the initial light intensity. Today, many techniques can be used to achieve polarization, but most fall under three categories: polarization by absorption, reflection, or refractions. First, the simplest form of polarization, absorption, relies on the physical properties of certain materials to absorb light waves traveling in only some directions. This can be achieved with a wire grid polarizer and is a property of some crystals, including tourmaline and herapatite, but is more often associated with Polaroid, the trade name for iodine-impregnated sheets of polyvinyl alcohol. In all of these materials, the presence of long strands or molecule in a single axis enable light traveling in that axis to be absorbed, while that moving perpendicular to it cannot, allowing it to pass almost completely through. Effectiveness can reach more than 99% of parallel light, but light loss in the perpendicular orientation can be anywhere from 20 to 1% based on the thickness of the lines or molecules. This is why placing two pairs of sunglasses over each other has almost no effect if they are in the same direction, but as they are progressively turned until the angle between them is perpendicular, more and more light is blocked until it's almost all filtered out. Second, polarization can be achieved by reflection. This is because the coefficient of reflection of a transparent medium is different for parallel or p-polarized waves than for perpendicular or s-polarized waves. Therefore, at a specific angle, it is possible to not reflect any p-polarized light. Therefore, all reflected light will be s-polarized, although not all perpendicular light will be reflected. If this is repeated multiple times, one ends up with a series of diffuse s-polarized light sources, and with a beam of almost perfectly p-polarized light. For air and glass, the amount of polarization is around 16% of all s-polarized light for every interval. The angle in question is known as Brewster's angle, and for any two mediums can be calculated with the equation arctan of n2 on n1, where n1 is the refractive index of the initial medium, while n2 is the refractive index of the second medium. For glass, this is around 57 degrees. Finally, polarization can be achieved by refraction. Indeed, some mediums have the unique property of having a refractive index that is not the same for light of different polarization. These materials are known as birefringent polarizers, and they have two indexes of refraction which effectively split all light coming through them. This is often found in anisotropic crystals, such as calcite, where the physical structure of the crystal matrix is uniaxial, and therefore it forms an optical axis. Indeed, light traveling perpendicular to this axis is refracted as normal, the normal refraction index in calcite 1.658, while light traveling parallel to the optical axis behaves differently, an extraordinary refraction index in calcite 1.486. If the separation between the two polarizations of light is great enough, any produced image will appear duplicated, with each being formed of light of inverse linear polarization. Therefore, if one observes the image created by a birefringent polarizer through an absorptive polarizer, one will only see one of them, depending on the axis of the absorptive polarizer. Furthermore, as the refractive index of the material changes based on the orientation of the light, the angle required for a total internal reflection changes. This allows for the reflection of a single polarization of light at all angles in between the two critical angles, creating two distinctly separated images of different polarization, with one being reflected and one refracted. In calcite, this difference is 5.2 degrees, and is a phenomenon observable in the Nicol, Wollaston, and Sinarmon prisms.